All right, gang, Mass 6500. No music this time, sorry. But I listened to what you guys had to say about what you preferred in terms of putting up the lectures. And it seemed to most of you, at least the ones of you that commented, said you kind of preferred this method. So uh, aim to please, and so that's what I'm going to use probably from here on out. There may be times that I still use the Blackboard, but it'll just depend on the nature of the lecture. Guys, what we're doing in this video is what we call the coefficient of multiple determination. Some of you in the previous video were just dying to use this R squared stuff, so I thought, well, let's. To be honest with you, I was going to skip this, but it seems like some of you are kind of fascinated by this thing, so let's go for it. As it turns out that the extra sum of squares probably be really handy if you guys could see that, wouldn't it? The extra sum of squares that we've examined over the last couple of weeks is not only useful for testing coefficients, and what I mean by that, it's not only, and obviously I'm talking about regression coefficients here. So it's not only useful for testing whether an additional coefficient should be added to the model or whether one should be dropped. It also has ramifications and some useful properties for examining the coefficient of multiple determination R squared. Now, not really sure where I want to go with this. Let's think about the simple linear regression model, and let's say, for example, that we get an R squared equals 68%. Now, guys, again, simple linear regression model. We're just talking about we have one predictor, x1, on some dependent variable y. Well, what we would say here, if R squared is 68%, we would say that 68% of the variance in y is explained by the regression on x1. And this is assuming that our full model is a single predictor model. It's simple linear regression. Now, slightly more going on when we get into the multiple regression case. So, guys, for the multiple regression case, the multiple regression model, let's assume that we have the full model being, oh, I don't know, we can start out with as many predictors, I guess, as we want. Let's look at the three predictor model. And let's say in this situation we have an R squared equal to 68%. Now I'm running out of space down here, so let's start a new sheet of paper. Get everything lined up here. Okay, so in this situation, what we would say is that, what did I say, 60? I forget, 62 or 68, 68%. Don't guess it really matters, but let's get centered up here. So what we would say in this situation is we would say that 68% of the variance in y is explained by the regression on the set of predictors x1, x2, and x3. Now, it may be pretty obvious to you that our next step is to examine the change in r squared as we add a coefficient. So I think this is an obvious next step. Not really knowing what is coming next, you would think that that's an obvious next step. And that would be to examine the change in the multiple r squared when an additional, or we could say when additional, but we're going to focus on the simplest case here, just when we add one coefficient. So when an additional variable is added to the model. Now, guys, it's important to understand what we call this. When we have, for example, the full model, then as we talked about earlier, we call that the coefficient of multiple determination. However, when we want to examine the addition of a variable, we call this the coefficient of partial determination. Let me get this down where you can see it. So again, just simple difference here. Multiple determination talks about the full model. Partial determination talks about the change in the multiple r squared when we add a model, or when we add a variable to our model. Now let's jump in and look at an example. That's one thing I've really tried to do more of in 6500 after I've had a chance to think about what I did in 5500. I'm trying to use more examples, so hopefully I'm successful. Now let's say our full model has two predictors. So at this stage of the game, I would expect you to know that our full model would look like this. I would also expect you to know that, for example, excuse me, that the sum of squares for x2 measures the variation in y when x2 is in the model. I would also expect you to know that the notation sum of squares error for x1 comma x2 measures, it probably goes without saying, but I'm going to be thorough here, measures the variation in y when x1 and x2 are in the model. Okay, so just a little bit of review there. So let's consider the case when, I don't know how we want to go here. Let's just say when x2 is in the model, and we want to examine adding x1. Well, what's going to be the natural progression here? Well, that's going to be just like before. Let's examine, take a look at the sum of squares for the error. Let's get everything separate, situated here. All right, so what I would want to do is I'd want to look at the sum of squares that's going to be the largest value. And so we've got x2 in the model, and so that's going to be when the error is going to be the largest when we have the single predictor, minus the smallest standard error. Remember, standard error is going to decrease, or at least it's going to stay the same or decrease for the full model, over the sum of squares error just for x2 being in the model. Now, we should know now from previous lectures that the sum of squares error for x2 minus the sum of squares error for x1 comma x2 is nothing more than the sum of squares regression for x1 added to the model when x2 is already in the model. And there will be no change in our denominator. We just have the sum of squares error for x2. So getting this getting this back into the form of kind of the S statistic. Now, guys, remember this R squared is a descriptive statistic measure, so we don't have any underlying probability distribution. We're not trying to find p-values. We're just trying to explain the relationship, if you will, between the set of the values that we've collected in our data set. Again, we're not trying to generalize this to a larger population, so keep that in mind. These are descriptive statistic measures. Now, having said all that, let's take a look at at what we had and what we've now created. Now, what we had before, let's say that our full model is a 2 predictor model. Okay? And just so there's no confusion or misunderstanding, I want to give kind of a 2-column. On the left-hand side, I want to test adding a single variable. The guys over here are F statistic, and we call it F star. It's the partial F. Would be the sum of squares error. What I want to do here, let me be. Let's stay consistent with what we did before. Let's say that x2 is already in the model, and we want to look at examining the effect of adding x1. Okay, so I would have the sum of squares error for x2 minus the sum of squares error for the full model over the degrees of freedom. Divided by sum of squares error for the full model over, so we got two predictors, so n minus 3. Now this part right here, we should know by now, comes to the sum of squares regression, adding x1 with x2 already in the model, over degrees of freedom 1, adding one variable, and over the sum of squares for the error for the full model over n minus 3 degrees of freedom. Now that's where we've been. Okay? Let me, probably going to help if you can if you can see that. Now, where are we headed? We're headed to look at this multiple r squared. And when I compare where we've been to where we're going, and again, remember, this is an inference procedure. This is a descriptive statistic measure. We're just describing the relationship from the data that we've actually collected. So, guys, we take out our degrees of freedom, and it turns out that the right-hand side just has sum of squares regression for x1 added to the model with x2 in it. So really, in a lot of ways, except for eliminating the degrees of freedom, the the numerator looks the same, but the denominator, we not only reduce take away the degrees of freedom, we just look at the sum of squares for the reduced model, just having the initial predictor in it of x2. Guys, that notation can sometimes get a little confusing, so that's why I want to point that out to you. Now, what I'd like to do now is, hopefully, I've still got body fat on on my desktop. So, and I'm pretty sure I do. So let's take a look at a 3 predictor model. And one thing about this way, you guys get to see my hand a lot, don't you? So let's take a look at the 3 predictor model. And, guys, what I want you to think here is to think the body fat example. If you remember, body fat, the dependent variable was a measure. The body fat measure, I think this was a tricep measure. I think this was a thigh measure. And I think this was some sort of mid-arm measure. So we want to look at this and use it as an example. So the example I want to look at Let's say that the model contains, it really doesn't matter. Let's just say, keep it simple, x1 and x2. And we want to examine the change in the multiple r squared when adding x3. Now, get into some notation here. The notation in this case would be r squared. In the subscript, we're going to have y, and we're going to put the variable that we're adding, which in this case would be 3, given the other variables that are already in the model. So this is the way that we talk about looking at the coefficient of partial determination given variables 1 and 2 already in the model, and the addition of variable 3. Now you should know that it's going to be the ratio of the sum of squares error, sum of squares regression of sum of squares error. Now I'm going to pause here and I want you to think, what's going to go where? Guys, what's going to go in the parentheses for the sum of squares regression? What's going to go in the parentheses for the sum of squares error? Well, guys, it should be pretty clear the sum of squares regression. We're going to look at the addition of x3 with x1 and x2 already in the model. And pretty much you can always be, in this case, that whatever is in the model is going to come down to the sum of squares for the error. And guys, again, this is called the coefficient of partial determination. Because you can really drive yourself insane if you think of this as the coefficient of multiple determination. Because our outputs in R give us the coefficient of multiple determination. And it's so tempting to just look at those and look at how much they changed. That's not what we're doing here. We're looking at the coefficient of partial determination, which gives us a different measurement. Now, what I would like to do is bump out of this. And hopefully I've got R up. Maybe not. No, I don't. And let me make sure I've got body fat. Yeah, there it is. Okay, cool. So let's do the standard stuff. This is where we need some music, isn't it? All right, guys, so I've attached the data and the names are, see how everything's spelled, so no capitalization. All right, gang. So the first thing I want to do is I want to create the sum of squares error for x1, x2. So I'm going to call this my first model. So I'm going to run a linear model with body fat as a function of triceps plus thigh. All right, I can do summary of my model. I really don't need it at this stage, but I want you to be aware of this. And I can run ANOVA of my model 1 and get what I need, okay? So guys, in this situation, I can see that my sum of squares error, x1, x2 is going to be 109.95. So I'm going to write that over on the piece of paper, and we'll go there in just a second. Now, the sum of squares regression for x1 and x2 is going to be the addition of these two values right here, 352.27 and 33.17. So it looks like 385.2 44 would be the sum of squares regression. But guys, what we want in the numerator is we want the sum of squares regression when we add x3 to the model when x1 and x2 are already in there. Well, guys, that's going to be easy to find too. So we'll just create another model. And I'm going to cheat just a little bit here. I'm going to go up and copy that. So all I need to add is what we call mid-arm. All right. Yeah, I want just go ahead and cut to the chase here. So model 2. Now I can see that the tricep and thigh sum of squares haven't changed, and you know that's what you would expect. And so by adding the mid-arm, we have added 11.55 sum of squares to the regression, thus subtracting 11.55 from the residuals. Now we don't actually use this measurement here. All we're going to use is 11.55. So guys, ultimately our coefficient of partial determination here is going to be 11.55 divided by 109.95. So guys, what we end up with here is 10.5% as our coefficient of partial determination. Now let me get back to this, and you can see that that I've just made the simple calculation right there. Now, you know, what does this tell us? Well, it depends on the way you want to look at it. It depends on the way that you want to produce your interpretation. One way is to focus on the percentage of variation in y that's explained. So I could say then that the percentage let's see, is my focus, yeah, there we go. A variation in y when regressed and remember x1 and x2 are just tricep and thigh. So the percentage of variation in y when regressed on x1 and x2 is increased by another 10.5% when x3 is added to our model. Now that kind of focuses on, in many ways, it focuses on the total variation. We've also got an interpretation here, and probably one that's maybe a little more appropriate. I'm not. But we got one that focuses on the sum of squares for the error. So we could say that the error sum of squares for the model containing x1 and x2 is only reduced. I'll tell you what, I don't like the word only because that's kind of leading, I think. So let's keep things interpretations more vague in general. So is reduced by another 10.5% when x3 is added to the model. Okay, and guys, I'm gonna point out one more time. I've said it, but I want to be redundant here. We have no p-value. This is a descriptive stats measure. No generalization here, gang. Just describing the relationship. Now, it turns out we can take this just a little further, and we're going to. But you know, you would expect that back in the simple linear regression case, that when we're given r squared, the coefficient of determination, that we could take the square root of r squared and get what we call r, which is the coefficient, the correlation coefficient. Well, it turns out that we can do the same thing here. We just give it a little bit different names and a little fancier names, I guess you would say. So it turns out that the square root for the coefficient of partial determination which we know in this case was equal to r squared y, adding 3 to a model where 1 and 2. I don't really know what you would do here. Just hit me. What would we do if we had like 15 predictors? How would you do 1, 2, 3, 4, 5? And by the time you got to 11 and 12, I guess you'd have to start using commas. I don't know. So guys, what we would get here is we would get the plus minus. Now I'll explain that in just a second. I'm not talking about plus minus in terms of that's our answer. We have to choose plus or minus, and this is based on our beta. And I'll give you an illustration of that in just a second. Okay. So this is just going to be plus minus this particular value. So gang, in our situation, let me get my calculator. We're going to have plus or minus the square root of 0.105. So this is going to be plus or minus 0.324. Now, how do we determine plus or minus? Well, what we do is we take a look at the sign of the coefficient in the model when, for this situation, we are looking at the variable x3. So we would look at the sign of beta 3 when it's added to the model when x1 and, well, beta 1 and beta 2 are already in the model. So let's go back to our output for r, and we can see that we can't see anything because we haven't done it yet. So we need to do the summary of our model 2 and look at the coefficient of the sign of the coefficient for mid-arm when the other two are in the model. So the mid-arm coefficient is negative 2.186. That's going to determine what the sign of our coefficient is going to be. So guys, in this case, we're going to have negative because beta 3 was negative. Okay? So our our, 2 2 partial correlation coefficient for adding mid-arm with thigh and tricep in our model, it would be 0.3 or negative 0.324. Now, gang, it turns out that our coefficients a partial determination. I wonder if you guys get tired of looking at my hand. I can tell that I've got a lot of sun damage. I don't guess it really took this for me to know that as much as I'm outside. But anyway, coefficient of partial determination can be expressed as partial correlation coefficients. Now, for the most part, you can probably just store this in your trash can of useless information. I can't really imagine a situation where we're going to need this, and I have to confess to you, I didn't remember this. This is one of the things I had to look up. Some of this other stuff, I remember quite well, I think, at least. I had to look up. So, guys, in our case, when we have the partial, the coefficient of the partial determination, just over here where you can see it, for y adding 3 for the model 1 and 2, when variables 1 and 2 are in, we can look at this as the correlation of y3, 1, 2 quantity squared. And I'm going to give you this. Again, I haven't really decided yet what's on the next homework assignment. There may be something that uses this, so I'm just going to go ahead and give it to you. And certainly don't take up brain space memorizing this thing. I didn't. So again, you might store that in your trash can of useless information. And then there might be a situation on your next homework assignment where you need that. Just haven't really decided yet. So, gang, that's it. End of the video. Next time we get into, I don't know what we'll do next time. Probably getting into, probably standardizing our regression models. For example, so say you've got a model that has ACT and SAT in your model, and you're trying to predict something. Maybe you're using both of these measurements to predict first-year college GPA or something like that. Well, ACT is measured from, I guess, 0 to 36, probably 1 to 36, while the measurements on SAT are much larger, 1,200, 1,400. I think they go all the way up to 1,600. So you think about when we interpret the coefficients, 1 unit increase in an SAT score is minimal, almost irrelevant. However, a 1 unit increase in ACT could mean something. 31 to 32, for example. I have a good friend whose daughter took the ACT numerous times because the school she was trying to get into required a 32 for full ride, and she was on a 31. So, guys, anyway, that's probably what we're going to be doing next. So, take care.